All right, welcome back. Let's do some more calculus. In our second lesson this year, we're going to talk about limits analytically. This is a little bit more challenging than just the limits graphically, where you get to have a visual representation. This time we're going to use some algebra skills and how to solve limits and evaluate them. So to start us off, let's recall what in the world is a limit. It is the y value a function approaches at a specific given x value. So if you think back to our last lesson, it would probably make a little bit more sense when we're talking about the y value we're approaching. So how are we going to find limits? We have three main ways that we find a limit analytically. The first thing is direct substitution. It is so easy. You're going to love that one because it really is the easiest thing on the planet. And then next we're going to try and simplify, and then we will try direct substitution. Now I have the simplify thing broken down into two different parts. The first way is to try to factor and cancel. Now here's the reality. I cannot list every single possible way of trying to simplify. It's just not going to be possible. But these are the common ways: factor and then cancel. If I was to list every possible example in this lesson, this video would be 45 minutes long, and really none of us want that. So then the next thing is rationalizing. When you see square roots, most likely you're going to try to rationalize. If you've tried direct substitution and it doesn't work, then we'll come back and we'll rationalize. And as always, usually this makes more sense after you've tried a few problems. So if you want to rewatch the very beginning of this lesson, then it will kind of summarize what we're going to do throughout the whole lesson. And then number three is something called l'hôpital. I think that's how you say it. He's a French guy. L'hôpital, l'hôpital. I don't know. L'Hopital's rule is usually how people say it. That's only for forms when we have 0 over 0. So if you try direct substitution and you get 0 over 0, or you get infinity over infinity, usually it's 0 over 0. It happens all the time. You got to use a shortcut, a really fast shortcut called L'Hopital's rule. Here's the bummer. We're not going to learn it today, the shortcut, because it's not until we get into Unit 4. Oops. Unit 4 is where we're going to learn L'Hopital's rule. But the idea is, if you get to the end of this course, you're studying for an AP exam, and you're looking back over notes how to find a limit, the idea is you see this and you're like, oh yeah, you could use L'Hopital's rule when you're reviewing. But we're not going to use that yet in this lesson, but we will cover it in Unit 4. So let's start off with the easy ones, direct substitution. So we have this expression here, x squared plus 2x minus 4, and we're going to try to just substitute in the limit at x as x approaches -1. So just substitute that puppy in. -1 squared plus 2 times -1 minus 4. -1 squared is 1, minus 2, minus 4, and then all this simplifies down to, let's see, -6 plus 1, -5. Okay, so that's the answer, -5. We just did direct substitution and we're done. But I want to show you what the graph looks like. And you see here, this is just a parabola, x squared plus 2x minus 4. Here's the parabola. And at the x value of -1, we have a y value of -5. So that is what what we're looking at, the y value. That's why the answer is a -5. Okay, let's get rid of that and try example number 2. And again here, we just do direct substitution. So we're just saying if the limit as x approaches 2, so x becomes a 2, you plug that in to see what the y value is, and we get the square root of 6 minus 2, which is the square root of 4, which is 2. So easy and simple. Let's take a look what the graph looks like. And there we go. So what's going on here? If the x value is a 2, you can see here that the y value is also a 2. And the coordinate point's down there at the bottom of the screen. Okay, so that's direct substitution. It is as easy as we can get for these types of problems. Now let's try something a little bit more complicated, which is factoring. So the strategy here is you cannot use direct substitution because if you plug the 0 in, you get a 0 on bottom. So limit as x approaches 0 of, we're going to factor everything that we possibly can from the numerator. The only thing they have in common is an x, so we'll factor out an x from each of the two terms here on top, and then you still have the x on bottom. And now the nice thing here is that all you have left here after those x's cancel is you just have a 4x minus 5. So then you do the direct substitution, 0 gets plugged into this x, and then you're allowed to do that. So after you simplify, you try direct substitution, and then you just go straight to that answer. You can see here it's 4 times 0. I probably could have written that 4 times 0 minus 5, and then that gives you to -5. All right, so let's try number 4. Why don't you try to do this one on your own? I will pause here, and I'll have the answer and my work show up. So just try to factor it, cancel what can cancel. And there we go, negative 15. So you can see here you had to factor the 2x minus 1 and an x plus 7. That's how the numerator factored. The x plus 7s would then cancel, and then you just use direct substitution to get the negative 15. Now what I haven't shown you was the graphs. I'm going to show you the graphs of these things. So let me have both of those appear. Okay, you can see this first one. Here's the graph, but you've got x, when x equals 0, y equals nothing. For this graph. Same here, you've got x equals negative 7. We're looking for when the x value is negative 7, and the y value is nothing. We don't know what it is. Why can't we see a negative 5 and negative 15? Because you're not allowed to plug a 0 in here in the bottom, and you can't plug a negative 7 in here in the bottom because you get a 0. So what we can do instead, let me pull up two different graphs. Now on these graphs, you can see what I did is when I did the trace for this one, instead of plugging in x equals 0, I did 0.001. And then that way I was really close to 0, but not exactly 0. Then you can see what the y value is close to, which is negative 4.996. The closer to 0 I get, the closer it'll be to this answer. Same over here. I went really close to negative 7, and then you could see the y value was really close to negative 15. Now, you won't be using calculators on this assignment, nor on the mastery check, but the idea is if you needed to double check yourself, you could see what the y values are just by plugging in this into y equals, graphing it, or using a table of values, however you want to do that. Next up, rationalize. Okay, here's what we're going to do with rationalizing. When you have a radical, this square root stuff, and you can't plug the number in because you get a 0 on bottom, what we do is we are going to multiply by what's called the conjugate. So I take the square root of x plus 4. But instead of a minus, we're going to put a plus 3. And if I do that on top, I must do it on the bottom. Or plus 3. So how do I know what to write here? It's always going to be the opposite of this. Let me give you a quick little reminder of why I'm going to do that. Because if you have a minus b, and I multiply it by a plus b, if I were to distribute this, multiply it out, you'd get this, a squared minus b squared. The two middle terms would cancel. This is called the difference of two perfect squares. So by multiplying by the conjugate, top and bottom, what you're really going to get is this whole thing is a, this whole thing is b. So this whole thing is a, this whole thing is b. So on our next line down, we'll go the limit as x approaches 5, long fraction, we get a squared. So the entire radical disappears because it's being squared. So it's x plus 4 minus, and I'm putting in parentheses, 3 squared is 9. Okay, so it's just the a squared minus b squared. That's what multiplying by the conjugate does, is it cancels out this square root symbol. Now on bottom, there's no need to multiply out anything. You're just going to leave this in groupings, and then we have square root of x plus 4 plus 3. Let me skip down here to the next line to clean this up. Okay, and then the point of this is now you've got an x minus 5 that is going to cancel with that x minus 5. And this thing's going to clean up quite a bit now. We can take the limit as x approaches 5. You can just do direct substitution. So this is going to equal, what is our numerator? 1 over the square root of 5 plus 4 is 9, plus 3, and then that equals 1 over 6. All right, there we go. That is how you do the strategy of rationalize when you have to rationalize or multiply by the conjugate, top and bottom. Some of our problems, like number 6 example, will have two variables. So you'll have maybe an x and an h is very common to have, and one of them will be approaching 0. So if we could try direct substitution, 0, 0, that's all good, but you can't have a 0 on bottom, so it does not work to do direct substitution. So instead, what we're going to do is multiply this whole thing out. Now, let me remind you, because it's for some reason, I don't know why this happens every year, but we get calculus kids who forget what this means, x plus h squared. Do not distribute here and here. Don't do that, silly. That is not correct. Please, please, please. So the idea is it's x plus h squared. It means there's two of them. That's x squared plus 2hx plus h squared. That's what that equals. So let's write down our first line. We're going to simplify this whole thing, and what are we going to get? Voila, this monster. So all this is, I multiply this out, distributed the negative 3, distributed the negative, and then you get this thing. So go ahead and write that down if you don't have it yet, because then I'm going to go ahead and keep working here and try and combine like terms in the numerator. So we have this long fraction, and x squared is going to cancel. What am I going to have left? All I'm going to have left is 2xh plus h squared. I can see here there's going to be some things that cancel, so you got to look through there. If you need to cross them off with your pen or pencil, then go ahead and do so. And then you'll come all the way down to this. So that's what that fraction simplifies to. So the next step is, since we still can't use direct substitution, because you'd get a 0 on bottom, what we'll do is we use our strategies from before, which is factoring what we can, and each of these terms has an h. So what you're left with is 2x plus an h minus 3. When we factor out an h from all of those, then you can see that h and that h will cancel. Now we use direct substitution, plug in an h into that 0 spot right there, or 0 into the h, and your final answer is 2x minus 3. That is our answer for this one. So you'll have your answer, instead of being a number, like in our previous problems that we did, we'd get the number 1/6 or whatever they were on the previous examples. Now we have an expression with an x variable in it. If we start off with two variables and only one of them is becoming 0, most likely you're going to have another variable in your answer. Next up in our lesson is dealing with piecewise functions and limits and how we handle that situation. So if you look here at number 7, it's saying that we're going to approach -5 from the negative side, meaning the left side of -5. So here's our function, and since we're approaching -5 is the breaking point here. It's where the graph changes. So here I gave you a graph. Having a graph is not necessary. In fact, usually you won't have a graph. I just gave you one so we can look at this visually here. So here's our -5 x value, and we want to approach it over here. So we're approaching from the left side and approaching that way till we get to that point. So whatever this y value is the answer. So that means which of these pieces? The x value that is less than -5. So if we plug a -5 into this thing and simplify 11, well, here, let's just do it real quick. 11 minus a -5 means 11 plus 5, which is 16. So we have square root of 16, which is 4. So that is approaching -5 from the negative side. Now let's approach -5 from the positive side, meaning the right side. That's just this other one. So if you plug this whole thing in here, what's this going to be? The graph makes it look like it's a value of 0, but I'm pretty sure it's not 0. So let's try this out. -5 plus 3, let's see, 5 minus a -5 squared. That's going to equal -2 on top. Down here, we're going to get 5 minus 25. 5 minus 25 is -20. So this fraction simplifies to 1/10. All right, so that's our answer there, 1/10. Now here, if we want the limit to approach -5 and you see no symbol, what does that mean again? It means we're approaching it from both sides. And since the left side is not the same thing as the right side, the limit does not exist. These two sides are not coming together, and this is how you show it algebraically. So here is an example for you to try on your own. I want you to do the g of x1, 10, 11, and 12. I'll pause now, and I'll have the answers appear in just a few seconds. Okay, so number 10, we're approaching -1 from both sides, which means here's the -1 and -1 jump between these two pieces. So you had to plug the -1 into this x value and this x value, see what the two pieces equal, and they both equal 3. So that's why the answer is here. Now number 11, I could see some students struggling with because of their logarithm properties. Let me show you what that one would do. Natural log of, plug in the e, you get e cubed. Why did I do this one instead of the middle one? Because it's from the positive side of e, the right side of e. Now that, if you remember your logarithm properties, you can bring an exponent to the front. The natural log of e is 1, so this is 3 times 1. And then the last one does not exist because these two pieces do not exist. All right, so we're done with piecewise functions. Let's do the last part of our lesson, and that is dealing with special trig limits. Now, I'm sorry, but you just got to memorize this. It's not that hard to memorize, but you do have to memorize this. the limit as x approaches 0 of sine x over x. It equals 1. Or you could say x over sine x, it also equals 1. Doesn't matter which way. So the x can go on top or bottom, but that thing equals 1. Here are the graphs. You do not need to know the graphs. I just put them here so you can kind of get a quick little visual representation. And as we approach 0, you can see here the point is approaching this value, which is 1. And same thing on this one. It's approaching a value of 1. Again, you don't need to know what the graphs look like. You just need to be able to memorize that these things, what they equal. And then the other ones, with the cosine, 1 minus cosine x over x is 0. Cosine x minus 1 over x also equals 0 if we're having an x value approaching 0. So again, here's the two graphs. This is what they look like. Not necessary to memorize it, but it's just so you can see they are approaching a y value of a 0 right there at the origin. There is a hole there. There's a gap, so it doesn't actually equal 0 if you plug in a 0 to x, because you can't. Okay, so important stuff to be able to have those memorized. A suggestion to you to help you. Here's the way I remember this. Sine has the number 1 in it. So the sine x over x is going to equal 1. And cosine has a 0 in it. So the cosine, the one that has the cosine is going to equal 0. You just got to remember, and this is where this doesn't work so well, but the cosine x is attached with a minus 1. So it's either cosine x minus 1 or 1 minus cosine x. Just remember that. This one's a little easier though. Sine x over x or x over sine x equals 1. So let's use this stuff for our last set of problems. Okay. So we have a 3x here and an x on bottom. We need these to be identical, because if you look back over here, this was x over x. So if the angle is 3x, we need this to be a 3x as well to make this whole thing become a 1. So let's just give it a 3. You're allowed to do that. You could just give it a 3, multiply it by 3 on bottom, and then you'd have to multiply by 3 on top as well. So that now becomes the limit as x approaches 0 of 3 sine of 3x over 3x. Now this piece right here that I'm circling, that is a 1. Because sine of 3x over 3x, since the angle is the same thing as the thing on bottom, that equals 1, and all you're left with is the limit as x approaches 0 of 3. This 3 right here. Well, and then that's easy. That equals 3. Man, seems like a lot of problems in these notes equal 3. That was not on purpose. Okay, that's how you do number 13. Now that seems like kind of as we do more of these, you'll think, oh man, I can see what the answer is supposed to be. Do I have to do all this work? Yes, you do. You got to show your work on this. All right, number 14. So tangent. How do we deal with this one? This becomes, let's change it so that it's sine 4x over cosine 4x, because that's what tangent is, sine over cosine. And then instead of dividing that whole thing by 8x, let's multiply the reciprocal. So instead of dividing by 8x, I'm just going to multiply its reciprocal 1 over 8x. That'll help separate these two fractions a little bit. Okay, so now we're going to have the limit as x approaches 0 of, I'm going to take the 8x and bring it over here underneath. You're allowed to do that because it's multiplication, and that's just commutative, fancy word for you there. Commutative means you can rearrange the order and it does not affect it. So then this becomes 1 over cosine 4x. All right, we're close. We're almost there. If this thing equaled 4x instead of 8x, then we'd be good because that whole thing would cancel off and equal 1. So let's make it equal 4x by multiplying by 1/2. And then if you multiply the top by 1/2, you have, excuse me, you have to keep it balanced. So then we'll have the limit as x approaches 0 of, let's see here, we're going to have 1/2 sine 4x over 4x times 1 over cosine 4x. And now you can see this right here is the same thing as the number 1. So you're left with, sorry, I ran out of room here. Let's just kind of go down a little bit of line. Now you can just do direct substitution because that thing's gone and we can plug a 0 into that. So we have a 1/2 times 1 over cosine of 0 4 times 0 is 0. And what's the cosine of 0? You got to be able to know those things, those trig, be able to plug in some main things from the unit circle. Cosine of 0 is 1. So this is 1 over 1, and that equals 1/2. Boom. All right, 15. This one's actually a lot easier than it looks because x approaches 0. It is just factoring. This is the difference of squares, the difference of two perfect squares. So we go cosine x minus 1 times cosine x plus 1, and then that's all over x times cosine x plus 1, and now you can see what cancels. Nice and pretty. Cancel, cancel. All you have left is cosine x minus 1 over x, and ding, ding, ding. Look, that is one of our, what do you call them? Our special trig limit identities. So this is 0. Cosine x minus 1 over x is 0, remember, because it has the cosine. Done. Okay, that's all of them. So I've not covered every single possible type of problem because or else this video would just take forever. But I've given you at least a lot of the tools that you need to try to solve these types of problems. And then again, later on in Unit 4, we'll talk about a shortcut that can help us out quite a bit with solving these things as well. All right, rock that master check. See you in the next lesson.